Good morning and welcome to the fourth edition of Save at Dead Fest Virtual. This is an event focused on technology and innovation, and this is an event that we have been organizing for 11 years now. So, for those who are not familiar with us, Save Software is a technology and innovation company that offers custom software development services, user centered design, digital transformation, DevOps, intelligent process automation, and agility. All the talks for today will be recorded, and you can replay them at your convenience on our YouTube channel at Save Software. We will have two thematic channels: the technical and methodological, and the UX and persona channel. You can check all the agenda of our talks at seva.com.co/SevaDevFest, and you can also find the topics in the description in this channel. If you want to make posts on your social media, you can mention us at Seva Software and use the hashtag SevaDevFest. To fully enjoy these sessions, we have some recommendations for you. Please be punctual, of course, that is important. Check your internet connection, find a quiet place where you can listen without any interruption. Leave all the questions that you have in the transmission chat. And afterwards, please don't forget to share with us your thoughts on the Seva Dev Fest. We're kicking this event with Jimmy Boger, who has 20 years of experience building mission critical applications and distributed systems, extensive experience with agile, test driven development, domain driven design, object oriented design, service oriented architecture, and distributed systems. And he has been awarded Microsoft Most Valuable Professional since 2009 and NS Service Bus Champ since 2012. And today he will be talking about advanced microservices messaging. You know that microservices introduce major complexities the moment we move away from a single service and process to multiple ones. So immediately the problem hits. Services have to communicate. The architect mandates rest, but nothing works in production. Then comes the events, but nothing is ever completed. So now what? What do we do in that case? Today, we will look at the problem more holistically. We want to uphold the fundamental autonomy of any microservice-based architecture while designing a communication strategy that would enable services to achieve their purpose in the world. That's where patterns come in. In this talk, Jimmy will look at some basic communication patterns, see where we might run into problems, and how advanced conversational patterns can help. He will walk you through some real world scenarios to demonstrate how complex coordination and conversation patterns can get service communicated effectively while retaining all important autonomy and use coping. So please welcome Jimmy. Without any further ado, the floor is now all yours. How are you?
I'm doing good, doing good. I guess we're actually in the same time zone. That's like almost never happens when I do these sort of things.
Yeah, never happens. That is so cool. So good morning for you also.
Yes, good morning to everyone out there. Yeah, so why don't we go ahead and get started? So yes, my background is in consulting, and so a lot of what I'll be talking about today is built on a lot of the experiences I've had with customers and with clients that are moving from basically a single kind of monolithic system, breaking down that system to smaller components, and then typically like each team is working on the individual services and components, but then they get to the end to put everything together, and then just like nothing works. And so as just going through these experiences many times with multiple customers of like everything looked good on paper, everything looked good on the whiteboard, but once we tried to bring everything together, nothing seemed to work work at the end.
Exactly.
So yeah, in this talk, it's a lot of experiences I've seen with those kinds of organizations and trying to understand where they went wrong with their design and how they can shift their thinking of their design to arrive at a better spot at the end. I call this advanced microservice messaging, but a lot of the patterns we're talking about really aren't specific to microservices. It's just the kind of the term that people use for these kinds of systems today. But a lot of the ideas behind microservices and service-oriented architecture are not new whatsoever. They're decades, and as we'll see, like even like centuries or millennia old, these ideas of autonomy and individual kind of workers doing their own thing. So a lot of what we'll be looking at is how we tended to solve these problems in the real world and applying those patterns into our distributed systems to be able to solve those problems in the kind of the virtual computing world. So first up, just want to kind of get out of the way, a definition of microservice. I used to joke that the term microservice, like was really ambiguous and no one really could describe what it meant or whatever. I think the guy that invented the term heard this a lot and finally wrote down on paper, okay, here's what a microservice is. So Sam Newman, the author of the microservices book, which are behind me somewhere in the bookshelf to make me look smart, he describes a microservice these days as an independently deployable service modeled around a business domain. And so there's a few key parts here. One is the idea of independence, that this thing can kind of live on its own and be deployed on its own. There's the concept of a service. And so his definition of a service actually comes from earlier art of the kind of service-oriented architectural land. And then there's the second part of this, which is modeled around a business domain. This is also an area where people kind of screw up microservices, is making them, really small or really fine-grained, where they don't map directly now to overall business domains. And so putting all this together, we want to arrive at a system that does preserve the autonomy and independence of services. And we also want to make sure that those map out to something in the business, that if the business looked at our systems, then they could say, oh yeah, that actually matches how we conceptualize things in our heads as well, that we're not making just kind of making things up as we go here. So yeah, I saw this kind of problem coming up even before the concept of microservices, when people were doing like building a lot of RESTful architectures before the kind of idea of microservices came around. And there's a few occasions where some folks spent, ungodly amounts of money building up, this new kind of business, this new kind of system that was meant to solve all the problems of their existing monolithic system. They go to deploy this into even like a dev environment, and they go to the page and just like nothing works. And all the developers and architects are confused. Like everything sure worked great when we're on our local system, like when everything is running on my laptop, everything worked great. But as soon as they went into a more distributed environment, suddenly the realities of distributed systems came crashing down on them, and their system literally just did not function whatsoever. And so from these experiences, I realized that they were building systems and modeling them in a way that could never work kind of in the real world. And if we think about microservices as these kind of independently autonomous actors or kind of, just these things out there that are just working on their own, I started to look out into the real world and realizing like, well, the real world does have a lot of these problems existing today as well, and have for centuries. The idea that the real world is messy, right? We don't have this kind of transactional guarantees in the real world. We can't get the entire world in a transaction to say, okay, everybody agree at the same time that this is the one solid truth. Is that there's always going to be delays in communication and things like that. And then we look at computing systems, the delays have become much shorter, but they still exist.
Yeah, you're right.
So I decided to look at it from kind of a slightly different perspective and say, let's try to look to see how real systems started out small and then grew, and then how were those systems able to scale out and scale up the work that they were doing, the processing they were doing, in a similar way that we're trying to then carve out these smaller boundaries around these individual microservices. So one good example of this is if we look at kind of like systems that existed before any kind of computing sort of things existed. And I think of things like restaurants, right? There was a time when there were no electronics involved in restaurants or fast food. Like fast food existed before the ability to have like electronic processing of any of this sort of orders. Okay. Or things like mail order catalogs. You used to have like these, I guess I still get these dumb things in the mail today.
Yeah, we do.
Yes. So you get these things in the mail, like it's already printed out, all the things that you could buy. And then, these days I would just go online and buy them. But you could like circle the things, fill out an order form, and then you mail the order form back in. And then sometime in the future, someone would process the order, and then you'd eventually get these items back. So those kinds of systems do have a parallel in kind of online systems. So things like Amazon.com or Zappos, these online retail stores, have a lot of the same problems that exist in those old systems of the kind of mail order, very slow systems. All those problems still exist. And so if you look at the architecture behind the scenes of these online systems, they're actually solving the problems in a very, very similar way that the kind of offline system used, but it's not necessarily something that you see or I see as a consumer. So as an architect, if we're trying to build these kinds of systems, our first assumption is to like, well, just build it like any kind of other transactional system. But these systems, these online systems, Amazon, what have you, their processing actually much more closely models how it actually was done 50 years ago versus as it is today. So I wanted to walk through an example in the real world of a system that does start small, and it closely matches the systems that that a lot of us deal with, these kind of like monolithic systems, and see how those like real world systems are able to scale up in terms of processing, in terms of throughput, things like that, and how they were able to divide and conquer and be able to get more business, and how we can apply those kind of lessons learned to the virtual systems that we're building. So I'm from Austin, Texas. We're a very kind of hipster, sort of place. And one of the things we have a lot of are food trucks. Food trucks are typically like, well, in the before times when we used to like go into offices all the time, we would have a food truck that would come out, on every day of the week, there was a different food truck, and it was some kind of hipster thing like Korean barbecue fusion thing. And it'd have like clever names for everything. And one of the things I noticed is that the system for those kinds of businesses very closely matched the kinds of systems I was dealing with, where they're like very small, and like everything was being done by sort of one process. So in this food truck, the one I was thinking of actually is fantastic. It was deep fried hot dogs, but wrapped in bacon. So they would wrap the hot dog in bacon and then deep fry it. So it's very, very healthy for you. Lots of good
Yeah.
trans fats or something. But this hot dog stand was run by exactly one person, which meant that one person did every single part of the business transaction. It also meant that everything was synchronous. So like you coming up to the counter, you would stay there at the counter for the entire order until it was complete. So you didn't leave that spot until you got your food. So this looked very similar to the kind of transactional systems that I deal with still a lot these days, right? I have a single application with, when I go to the website, there's a single, the single thread, or, I guess we're an async day, so maybe there's some awaiting going on. But me as the consumer of this application, I don't leave the web page until I get a response back. So it's a very synchronous request response. I make a request to the server. It does some work, but I'm just sitting here waiting at my laptop, at my screen, waiting for the response to come back. I get the response, and then I do some more work. So this is very, very similar to the kind of synchronous operation I was getting with the food truck vendor. Now, these food trucks are not cheap to run at all. Like there's all sorts of regulations. Like they're supposed to be like, they have the same kind of permits and all that sort of stuff as a regular restaurant. And you can even see it when you go up there. You'll see like in the back they have all like the kind of stuff in the back to say we have these permits to be able to do stuff. We get inspections allegedly of all of our stuff. It's supposed to be the same level of standard as a normal restaurant, just on wheels. So that also means that there's a if you want to go into business doing this, you kind of have to prove your business model, because it takes a lot of investment to be able to build one of these contraptions. You have to take a regular delivery truck and then outfit it to be a food truck with all the stuff that needs to happen for making whatever you're trying to make. So if I'm wanting to make this business, I have to understand, okay, well, if it's worth the investment to be able to do this food truck, I need to make sure that I can make money. And to understand how much money I can make, I need to understand, well, how many orders can I process using this model? So we can break down the ordering process into all the different steps it takes to complete an order. And I'm totally making this up, just because the math worked out well. So we can kind of break it down and say, well, I can only process one order at a time. So I need to understand how many orders I can process in a given amount of time. and understanding there's only so many hours I can be open, then that gives me kind of the maximum amount of orders and dollars that my business can make. So if we take all these different steps, taking the order, doing the different steps to prepare and make the order, and then giving the order to the person, we can come out and say, well, on average, this takes like 2.5 minutes, whatever. It's totally making this up. And then if we divide that out in an hour, you can say, well, then that means we get a max number of orders of 24 per hour. Now, if we looked at this and said, okay, I'll charge, I don't know how many dollars per order, and saying we're open for 3 hours at lunch and then 3 hours at dinner time, whatever, then that can give us like, well, we'll have a theoretical maximum of X amount of dollars that we can make in this business. Now, if we just went to kind of production with this assumption, we'll find that we'll never actually get close to this theoretical maximum number of orders per hour. And that's because the real world is way messier than this kind of concept of, people just file in and they get the order and then they're done. And it's it's different for different cultures as well. Like I give this talk in the UK and they love standing in lines. And so they're like, no, we don't mind, standing in line for queues. It's just fine. Where other cultures, they hate it. And, there's like a mad rush and then people cut and all sorts of things. So if we're looking at, how like the kind of reality of what we will see when we put this into practice, we'll see that, people are not as simple as just, the drawings we put on the whiteboard. Like most people don't like to wait. Although these days we all have smartphones, so we probably just like, checking Twitter or X, whatever we're calling it these days. But still, I don't want to wait a long time for my food. If I come up to decide I'm going to go down and get my food, and I see a long line, then I'll probably just walk away. So the original assumption here is that I kind of get one person coming every 2.5 minutes, but that's just not how it works in the real world. People don't leave to go to lunch at 1:07 and 30 seconds. They leave at kind of very normal times or very regular times. So they'll be going down at 1 o'clock or 1:15, whatever. They're not leaving at just kind of like randomly dispersed times. And oftentimes as well, when we worked in an office, we would have bursts of people coming down. Like I go to my Slack channel, the Austin Slack channel, and say, heading up for food truck, meet by the elevator. And then like 12 of us would meet by the elevator because then we could talk to each other, whatever. We'd all go down together instead of like, one person coming up every few minutes, and instead a big pack of people come down all at once. So if I'm coming down and I see a long queue and I've gone through this process before as a customer, and I can count the number of people in the line, and I can multiply in my head how long it takes per person, then I can, as a customer, easily figure out like, well, this is going to take like 30 minutes to get my food. I don't want to wait that long. So I'm going to do something else. I'll just go to my local sandwich shop, whatever, that is much, much faster. And so this business owner who does everything in the process sees this, and it's disheartening. It's discouraging to see here's someone that wants to buy something. I can see their disappointed look on their face, and then I see them walking away slowly and unhappy. And that's money that I've just lost that's gone out the door. Now, Amazon famously measured this. So they looked at their latency of their site, and they're able to determine for every X many milliseconds of latency what that meant in terms of lost dollars in revenue, because that person that wanted to buy something from their site, it was too slow and decided to go somewhere else or just not buy at all. And so they saw this and said, we're not optimizing for the right things here. We should optimize for taking orders and get as many orders as possible. But in this picture we have here, because this one person is doing every single step of the job, then it makes it really hard for them to be able to work faster and get more orders. Like, what do? They just like work faster and, don't finish the hot dog. And so you get like a soggy piece of bacon that's not done. No, they need to alter their business model and their processing so that they can process more orders. Now, one thing we could do is just say, well, let's just in quotes, let's just scale up or scale out. And instead of having one food truck, let's have 2 food trucks. And so now we can double the throughput because we have 2 food trucks side by side. And that helps to a point, but that's a massive amount of investment where we haven't really optimized for the problem that we were facing here, which is we can't take as many orders as possible in a certain amount of time. So the solution here is to hire more workers. And each of these workers you can think of as an individual microservice. Each one is an independently deployable component, a human being, although like don't ever refer to like delivery of human beings as deployments, unless you want to get slapped. But you can think of them as these autonomous workers that are doing their own thing, making their own decisions, and we need to have communication between these different workers, services, human beings in order to be able to achieve the overall end goal of I get my hot dog at the end. So in this picture, we now have each person doing one individual job. So they're doing one step in the overall process. And so I look at this as mapping to the business domain aspect of microservices, where this is an independently deployable human who is modeled around a business domain of they're doing kind of one step in the process here. This means, though, that each step in the process, because they're now optimizing their own domain outside of caring about what other folks are doing, is they can now do things like start multiple items in parallel. So previously, for example, the grill person, because it was also the ordering person, would only cook one hot dog at a time. In this picture, though, they can see a line of 12 people and they can drop 12 hot dogs because like this is a hot dog stand. Let's go ahead and start multiple of them at the same time. So they can start multiple items in parallel and optimize their individual job outside of worrying about what other folks are doing. This means now, in this picture, that ordering, the very first step in the process, is the only bottleneck for me getting money. Because now that very first step is me walking up to the counter, asking, telling them what I want, I give them the money, and then I'm done. So now we went from, we just had doubled the food truck, right? We would have gone from 24 orders an hour to 48. So, but that was a big investment just to get that doubling. But now, because ordering is a bottleneck, my max number of orders per hour theoretically shoots way up into like 120, because now I'm only looking at the amount of time it takes to do that ordering process. And we said 30 seconds. So if it takes 30 seconds to do the order, then theoretically I can take 120 orders per hour. This introduces a problem, though, is, well, how do we go about actually fulfilling this order? Because now we have all these people that need to communicate behind the scenes to be able to fulfill this overall business transaction of me getting a hot dog. So our transaction is no longer synchronous. We have a bit of asynchronous delays built into this processing. We need to understand how do later steps understand what to do? How do we know when we're done? And how do we get the order out to the correct person? And the solution here is going to be messaging and communication patterns. So let's look at each of these different interactions and decide from the kind of real world perspective, what is the correct messaging patterns and communication patterns for solving each of these different interactions. So the first one is just placing the order. We know what information we need from the customer, like what food you want. We also need to know how to notify the customer that their order is ready. And in the real world, what you typically see is a synchronous interaction. That is, the cashier and customer are blocked during this interaction. And the reason why we have a synchronous interaction is because it ensures a very low latency, very quick communication back and forth. If you were to do an asynchronous way of communicating, it would be something like the customer writes their order down on a piece of paper and then passes it over to the cashier. That cashier looks at the piece of paper, they write down another answer, and then pass it back to the customer while they're doing something else. So that's for the customer, they can be doing other things like checking their phone, whatever. But it means that it's a much slower interaction between the cashier and the customer. Since the cashier wants to accept as many orders as possible and answer any questions as quickly as possible, we have a synchronous interaction initially. It also means that we're using non-durable communication here, that we're not writing down our communication back and forth between the customer and the cashier. It's just verbal communication back and forth here. So that does mean that both parties need to be blocked, not doing anything else. It also means that they can't be, they have to be paying attention this whole time. So if you have a customer coming up and they're like checking their phone, reading emails, or whatever, TikTok, whatever, cashier's annoyed because like you're holding up other people in line while you're messing around your phone. So we do need to make sure that both of these different parties, the cashier and the customer, are fully engaged in this communication. So in the distributed world, like the customer is typically a human on an app, a web app, whatever, but we want to make sure that the web app is highly responsive and can get back those answers as quickly as possible. So first interaction, I want to place an order. So we said it's going to be a non-durable synchronous communication. So in this case, we, in the distributed world, we'd most likely use a REST or web API. So I would post up my order information. I'm Jimmy, I want a taco. And they'd get back to me, okay, I've received your information, and here's a link or URL for the status or information details about your order. So in this kind of interaction, we're going to be using a synchronous request response. So that was the easy part. What about these other ones? Do we use durable or non-durable communication? Who's going to be managing the steps, and how do we manage failures when something goes wrong? So when I'm designing these systems with clients, it's typically on a whiteboard, and we just kind of go through all the different possibilities and see what makes the most sense in terms of the overall business process, as well as the user experience. Because we can pick something here that makes sense from kind of a technology perspective that's kind of quote easier, but provides a terrible experience to the end user. So we have to balance those two things and make sure that whatever we choose here, the user isn't left out of the conversation, that we don't pick something that doesn't make sense and leaves them confused or annoyed or upset. So if we did this as a synchronous communication, right? So we receive the order and then we turn around and we send an API call to the dress service for dressing up the order, whatever. That means we have to worry about, just like in the real world, what happens if the other side is not paying attention? So what happens when we make a call to the dress service and we don't get a response? Because they're busy doing their actual work. And this happens a lot in the real world. Like I can see restaurants sometimes that are 100% verbal. They'll yell out an order, and if the other person doesn't hear or doesn't acknowledge that, then they have to like, oh, I got a service unavailable, so I need to retry. So I will keep calling that API until I finally get a good response, and then I can go on with the orders. So this is possible. We can do this with our distributed systems, but we have to worry about this whole like the service being down, not available, and what happens when we try to retry. Because I could have made the call to them, but they were just busy. They heard it, but they didn't have time to acknowledge it. So we now have to worry about item potency. Where if I said taco for Jimmy, and they were like, okay, I'm in the middle of making these tacos, but I'm busy, so I can't acknowledge them just yet. And then I hear again, taco for Jimmy. Well, does that mean that there were two Jimmys that wanted two tacos? Or was it the one Jimmy that wanted one taco and they just told me that twice? So in this kind of situation where I'm doing non-durable communication, if someone yells out Jimmy Taco, I probably have to yell out like, is that the same guy or is it someone else? Like we have to build those kind of things in, because otherwise we'll have two tacos and have waste, which maybe my cook doesn't care, like that's just like, more taco for me. But from a business perspective, we probably don't want a lot of waste there. We could do a sort of fire and forget. In this case, where I just say, order up, and instead of them making that taco immediately, they say, got it, and then sometime in the future, they'll actually make that taco. So this is something where like, if I yell at them, order up, they'll write it down on their side to do something, like make their own little to-do list, but they won't actually do the work immediately. So this is kind of very similar to the initial interaction as well. When I placed the order, I said I want a taco. They're not making that taco right away. So it's more of a fire and forget, where they say, yep, I got your order, order received, but I'm not making it right now. It'll be made sometime in the future. This is still acceptable from a kind of processing perspective, that they could write down the details internally, in a database or something, and then they're not doing the work right away, there's some other kind of background process that picks up the work and starts to then act on it. But we have to make sure that this interaction is okay from the the consumer perspective, that they're okay. Like, I'm asking you to do something, and I don't expect to have you do it right away. Instead, I expect to be, notified or some way of understanding that the order is done sometime in the future. So this kind of like verbal communication, synchronous request response, is how a lot of folks approach microservice-based systems, or even just services in general. They do a lot of API calls initially. They find that that doesn't work, and so they kind of swing the pendulum the other way and say, instead, we're going to do async messages for everything. So that does work well for a lot of scenarios, but we want to still make sure that we're choosing the right interaction for each step in the process based on the user experience requirements at hand, as well as the overall business, kind of the business needs as well. So how does this actually work in real life? Well, most restaurants I interact with, and most fast food even, they're not yelling at each other all the time. Like, it's not just noisy bunch of people just yelling back there. In fact, if I go up to the counter and I hear everyone just yelling out orders back and forth, I'm thinking, there is no way that my order is going to be correct, because people are going to forget stuff. They're not writing anything down. It's just going to be a mess. So instead, people write things down, because then you don't have to like remember things, and the other person doesn't have to be like listening all the time to make sure they get that response. So one great example here in Austin is a burger joint called Mighty Fine, who have Mighty Fine burgers. And one of the kind of interesting things that they have is their ordering system is also the food delivery system. So I'm showing here is a paper bag in which you, as the customer, you write your name on it, and then the bag turns around and you tell them what you want. So here we say, I want a cheeseburger, red, which is ketchup. They're being silly, with French fries. And so they don't want any. This might be a child, I don't know, because it's just cheese and ketchup and French fries. So yeah, you hear we're writing the order details on the bag itself. We're also putting some kind of information that signifies this person's order from someone else's. So the name Vanessa will then distinguish this red cheeseburger or ketchup cheeseburger from someone else's ketchup cheeseburger, which is not necessarily needed for each step up along the way, but for the final delivery process. And so this kind of process in which I'm including in the message all the steps that needed to be happening for that overall business transaction to complete is known as a routing slip. And in this case, it's an asynchronous durable message that includes the information, the kind of body, details about the order. In this case, I'm including a link that includes all the, here's go to this URL, hit this REST endpoint or a web API to get all the details. But the steps to process the order are in the message itself. So the very first step in the process, when we're seeing what they're ordering, we're including the steps in that message so that each step in the process does not need to know what to do next. They just look at the routing slip that says, okay, I'm the dress step. The next step says grill. So I just pass this bag to the next step in the process. If the order does not require a step, then we remove that from the process. So back here, if you didn't circle FF for French fry, this bag would not go to the fry station. The bag would go straight to the pack and deliver station, because no fries, no need to pass this bag along to that step. So this is, in this way, we have a queue for each step in the process. And you can physically see this, that you'll have a line of bags in each step that represent the work that needs to be done in the order it needs to be done. So they maintain that queue sort of aspect of the system. And for each step in the process, they're not directly like yelling out to each person, hey, order up. Instead, when someone is done, they take the bag and they put it in the back of the line for the next step in the process. There's no communication needed between these individual folks. So this means that none of the different steps in the process needed to be like blocked and waiting for responses from other different human beings there. They can work, not complete silence, because there's always some communication for the edge cases here, but they don't have to be for every step in the process. Make sure everyone is always online and available and responsive to communicate back and forth. So this gives us a bit of temporal decoupling, where I can drop that bag on someone's step, and then sometime in the future, that person picks it up. But in terms of me communicating with them, I am only blocked and the amount of time it takes me to walk from my station and drop the bag on their station. That's it. So if I want to make that step go faster, I guess I could walk faster, make the steps closer together. But otherwise, I'm not taking a lot of time just, communicating. I'm just dropping a bag over there. And the independence of each step is maintained. So if they want to, do 3 bags at a time, I'll look at the bags and say, oh, those 3 bags are burgers. So let me drop 3 burgers. Each step can decide what is the best way that they can process each step. We can also scale each step out independently. So if we have 2 grills and make a bigger grill, we can certainly do that. But that didn't affect the other steps in the process here. So this is kind of a very simplistic flow. And it works well if we have a very kind of linear assembly line way of working things, but that only works in kind of simple orders. So I wanted to turn it up to 11 here and examine how larger chains work. I'm going to use McDonald's here because I think everyone has McDonald's, just about. Fortunately or unfortunately, it's a kind of ubiquitous thing in the world these days. And so the larger chains don't work like this. They did initially. There was a movie that came out a few years ago, I think called The Founder, that looked at the kind of origins of McDonald's, of how it worked. And it used to be very much like this. They had a very simple menu. It's like burger, fries, drink, or shake, done. And so it's very much into, they looked at, how does Ford build cars, and they made an assembly line, which, that was novel for the time. But at some point, people were tired of like the same burger, fries, shake, and wanted different things. So McDonald's looked at this as well and said, we can't approach every single problem the same. We can't just have this assembly line because it's too inefficient for more complex orders, more complex flows. We want to sell more kinds of things, and the more complex offerings we give people, the harder it will be for us to be able to fulfill these order in this process. So in this case, we'll have many independent steps, but some are not independent. Sometimes there are dependency between different steps. And the steps can vary per order. Each order is wildly different. Someone may just order a drink. Some people may order, like I have a football team that's coming in, and we're ordering for the whole team, and so we'll have very big complex order, and we'll have some smaller orders. So how do we manage this? We can't just look at this, processing in the exact same way as we did before. We'll have to have some additional complexity in order to manage these more complex orders. So let's look. This actually worked in fast food. In a place in Texas called Whataburger, not McDonald's, but it was very, very similar. So I actually have some experience in how these systems work. So let's again walk through the process and see how it works in the real world and how we can model that in our systems. Again, the initial process is going to be a synchronous, non-durable communication. We'll have the person coming up to the cashier, telling them what they want, and that person is not preparing their order right then. Instead, they're just taking in all the information, writing it down, or persisting it somewhere. And they give the person back some kind of way to be able to be notified that their order is ready. Some places use natural identifiers or correlation identifiers. So like your name, like, the coffee shops typically do this, like mocha frappuccino iced soy for Jimmy. And then I know that's mine because there's not too many Jimmys in the world. But some of the McDonald's, like, they're more industrial, and so they don't care about your name. They just want, you're just a number to them. So order number 23, that's how you know. But it's still a synchronous interaction. We're not sending our order in via email or whatever. It is a go to the counter and I get my order. I know these days there are other, more complex ways. There are asynchronous ways of processing order. But that initial interaction of you telling the system what you want, that is going to be synchronous, whether you're doing it on your phone or whether you're doing it in person. The initial interactions are synchronous. Okay, taking the order easy, processing the order, that's hard. We already know that like synchronous communication is out the door. Like there's just no way this restaurant could survive with purely synchronous communication. The routing slip is too inefficient. If we just try to send a message along to each station or try to figure out ahead of time, that puts way too much burden on the upfront cashier to say, oh God, I got 16 Happy Meals and all this stuff. Like that's way too hard for them to figure out exactly how this order should flow through the system. So the solution here is going to be a conversation pattern. So the routing slip was something we could do with pure messaging. With conversation patterns, we actually need to blend messaging and databases and persistence technologies to achieve the overall goal of getting my order to the end person. So in McDonald's, the way it works is the very first step we do is we publish a message to all the stations. And the stations that are interested in this message or are going to be involved in the order will then queue up that message in their queue. And when I worked at Whataburger, I had like a screen above me that had all the orders coming in. And so when someone would place an order that was relevant to my station, boom, up on my screen at the end of the list popped up the order details. So that's our first step, is we just publish out the message saying order created. Here are the details of the order. Now, we could put the order items in that message. That's kind of a design decision that you will have to figure out between architects, whatever. Is it okay if we just put, here's the link to the order, and then you can go get the details that you want? Or do we kind of put all the details in there? That's kind of up to you. All right, so we need to have some way of knowing when this order is complete, because each of the steps can complete independently of the other. So the way that McDonald's handles this is when the cashier receives the order, what they'll do is they'll put a physical tray down. If you're eating in or if you're eating takeaway, you'll have a bag, and they put on that tray. The physical tray will then hold the items completed for the order. The receipt on the tray shows the details. So it shows like, here's all the items ordered. And now we need to understand, how do we coordinate these, the doneness of my order? So the way this works is a step will complete. The person making that individual step in the process will perform their step, and then they'll take the items for that step and then place the items on the tray. They will then check the items on the receipt for, quote, doneness to say, yes, is it good or not? And then if it's not done, then they go back and they continue on. Now, in actual like McDonald's now, there's a assistant manager doing this work. They're the ones that are shuffling the messages to the thing. So it's not each individual person's, like the dress person is just focusing on that. They have an inbox, they have an outbox, and they're just like doing the work and putting stuff in the kind of done section for their own individual station. And then someone else is coming in, collecting that and putting on the tray and deciding if it's done. So next step finishes, we place the item on the tray, we check the items on the receipt for doneness, it's not done, and so it goes on until finally, this last person making the fries checks all the items on the list against the items in the tray, and then when that's done, they say looks good, we ship it. They'll call out the name of the person or the number, and the person will come up and get their tray. So this kind of coordination in the microservice world is known as choreography. Choreography has event-based initiation. So we have a published event that goes out to multiple individual services, which means that the step order is not enforced between each step in the process. We have to track completion of this. So we have to know something needs to keep track of what things have finished or not. And this is also known as an observer, kind of the observer pattern. The thing that is performing the work, this human assistant manager that's going around to each station, gathering the items and checking for what's done. In the microservice world, that's known as a process manager. The process manager is managing the choreography, checking to see which things are done, and then when it's all finished, going out and saying, okay, looks good, go ahead and ship it. This also means that we have some additional state we're keeping track of, right? We have to keep track of that little receipt of what items are finished or not. That is something that, it's additional state outside of each step in the process that we have to keep track of and persist somewhere so that we understand when this overall process is done. And of course, delivery, as mentioned earlier, we need some way to correlate orders with people. We can use a natural correlation identifier, which is your name, or an artificial correlation identifier, which could be a number, or, our systems would typically use GUIDs, but I'm not yelling at GUIDs in a restaurant, so we'll just go with numbers. The other thing to note here is that this correlation identifier is not something that necessarily each of the steps cares about. So they may just, they do need to care about, because they need to know which tray to put the items on. So as they're bringing the finished items back, they have to put the items on the right tray. So this correlation identifier will also kind of be permeated throughout all the different messages in this overall process we're managing. All right, what about larger restaurants? So McDonald's is kind of optimizing for number of orders per hour. What about larger restaurants like sit down, sit down, eat in restaurants, dining in restaurants, not quick service or fast food, whatever you want to call them. In this case, the orders are much more complex, and the timing matters of these as well, right? We don't want to have someone's food come out before the other person's food. We want all the food to arrive all at the same time, because there's an awkward moment, and like someone ordered the steak well done, and that means we got to wait forever for that food to be finished. But they typically try to make sure all the food comes out all at once, and it's not sitting somewhere getting cold. So in this case, I need to have much more control over the process. That process manager needs to be much more involved in what happens when, versus the choreography where each step in the process was largely independent of the other. So this to me is more like the kind of benevolent dictator / chef, where they're the ones yelling out at people, I need this thing at this specific time, and they're really managing the entire order from start to finish. So this process begins with receiving orders, incoming orders from the waitstaff. They create a plan for completion, and then they're giving the orders to people at specific points in time to be able to get the orders to be finished at the same time to deliver to the customer at the end. It always, of course, starts out with an synchronous communication with the waitstaff. So me sitting at the table, I'm just talking to the waitstaff, telling them what I want. And then they're giving me, the communication back. So yep, got that. They're not necessarily giving me the bill, right? They may wait till the end because they can order multiple times throughout this entire meal. So they're just receiving the order details and writing it down on the little pad, hopefully writing it down. So in this case, I ordered a burger, ordered fries, and I order a pint of beer. And then at the end, they're like, okay, yep, I've received it. I've accepted your order. And now I'm going to walk back to the chef to then tell them, here's the order information. So in this case, a lot of times what they'll do is either punch it up in a computer, or they'll, their ticket that they've written down, the ticket actually goes to a till, like a thing. They put their order up, and the thing then rotates to the other side, to the kitchen, to be able to take it off the till and then be able to go process it. So it's typically an asynchronous durable interaction between the waitstaff and the back, because again, I need the waitstaff to be going out and doing the work. I don't want them to wait until someone's ready to hear their order on the other side of the kitchen. I just want them to hand off the order details and then walk away. Okay, so the chef receives this, and then they're going to start sending out the messages to the individual steps in the process. But instead of publishing an event to say, hey, order's done, like you decide what you want to do, instead they're directing each step in the process to do the work with messages. So they're going to send a command to each step in the process to do the work like now. So I say, make the burger, because burgers take a long time to cook. So let's go ahead and drop that down and get started on that. Someone orders beer, they don't want to wait for it. So let's go ahead and tell the bar to go ahead and make that pint so they can be ready for the person to deliver it. And then of course, we make money off alcohol. So let's get the beer out faster so they drink more and order more, that sort of thing. When an item is complete, I will reply back from that station to the chef or waitstaff, whatever, to say, hey, pint is complete. And then I will give a message to the waitstaff to say, go ahead and deliver this pint. Now that interaction could be done with an event. So this is something that I tend to go back and forth with my architects and tech leads to kind of go back both ways. Like, does it make more sense to have a reply back from this initial command? Or does it make more sense to have an event where maybe the person that is doing the work to deliver that item is not the same person that sent the original message in the first place? So it's a conversation with the developers and the team to understand what makes the most sense from a communication style. This one I'm just making something up and saying we are doing asynchronous request response or command reply or request reply to deliver the items to the person. Okay, so they send the pint to the person. We know that fries take less time. So now after the pint has been delivered, now I'm going to go ahead and tell the fryer to go ahead and drop those fries to be ready. And at this point, I told everyone what to do, And now I'm waiting for the notifications back to say these items are complete. So the grill person says, hey, burger's complete. I put it on that front counter there. Fry person says fries are complete, telling the chef that this is done as well. And then finally, once everything is complete, the chef says, okay, table 37 is ready to go out. And so the wait staff is told, 37 is ready. They take the items on the tray and then deliver that item to the person. This pattern, which is using commands mainly to direct each step in the process exactly what to do and when to do it, is known as orchestration. Orchestration, because you can imagine like the conductor up there, who is this benevolent dictator chef, they are telling each step in the process exactly what to do and when to do it. Each step in the process does not get to decide how and when it does things. They're being told what to do by this benevolent dictator. So usually this process is started by a single message. The message goes to this benevolent dictator. They're the ones making the plan, and then they're the ones that are telling everyone what to do. The person in green, the chef, is still going to be a process manager, but the process they're managing is orchestration. We use commands to coordinate. So I tell one person what to do, and then usually I'm using request response to indicate completion. So I send a command to a step, and then in the future, they will reply back to say, I'm complete, and here's the results. And then I can go on and do the rest of the work. And because this benevolent dictator this process manager is telling each step to do and exactly when to do it, there's a lot less tracking of status. Like I don't need to know what needs to be done when, because I know just by the nature of me sending a command out, when I receive the reply, I know that, okay, this step is complete. I don't need to keep track of which step is complete because I am the one deciding exactly what to do and when to do it. So when should we do this? When should we do orchestration versus choreography? We want to analyze the process flow and coupling between each step of the process, which usually means we will pick orchestration inside service boundaries because we want to have independent, autonomous services that can decide what to do and when to do it based on their own specific needs. That means that we don't typically want to use commands between services. I say usually because there's always going to be cases where we will have synchronous or asynchronous commands, but usually we would have commands inside of services, not between them. So that means that orchestration we would use inside service boundaries, and then choreography between service boundaries. So we would have events flowing between services because I don't want to tell other services what to do. Just like if I'm doing my own job in my company, I don't want other people telling me what to do. I want them to tell me, here's the work that needs to be done, and then I get to decide what the best way to do so is. So usually choreography between service boundaries. So just some parting thoughts here before we get to Q&A. When I see people screw these kinds of systems up, it's because they haven't thought about things in terms of those distributed systems constraints and the fallacies of distributed computing. Those constraints of the real world haven't changed. It's just gotten much shorter and smaller, but they still exist. They're still there. The way we can solve these problems in a distributed world can be applied directly from the way we've solved these problems in the real world, which is why a lot of those pattern names you see in messaging and microservices aren't just made up names. They come from things we actually do see in the real world. They're just applied to these kinds of systems. So if I look to see how the real world has solved these distributed communication, coordination, and conversation patterns, then we can apply those same kinds of solutions into a distributed world, and we are much more likely to succeed because we have already proven that it can work in the real world. And so can you. So with that, why don't we go pop over to Q&A, and I'll go open up the chat to see some questions we got here.
Thank you so much, Jimmy, for your time and for sharing your knowledge with us. I absolutely love the analogy with the taco food truck. It made me hungry, actually, but it was really cool. So for Q&A, I have a couple of comments and questions here on the chat that I would like to discuss with you. First, we have from William Schneider. He says a scale out versus scale up. Each has its purpose, advantages, and disadvantages. And of course, it's key to know when to use one or the other. Do you have like recommendations or good practice when how to use one
Yes,
another.
that's a great comment. So I would say, in our physical world, it's more difficult to scale up, right? I can't easily make a physical thing bigger. So our food truck, we can't make that food truck just bigger. That's much more
Mhm.
difficult to do. In a computing world, that is much easier, right? I can just slide the little slider over in the Azure portal and go from 2 cores to 4 cores. There's a dollar amount associated, so I try that first. Like if that's the easiest solution first is to say, well, let's quote just scale it up, and then when I look at when that breaks down, I can no longer be able to meet my business service agreements or my business needs. That's when I look, okay, then how do we break this problem apart into smaller pieces so that I can still achieve the goals from the business and user perspective, but also meet the tech constraints as well.
Awesome, great. And here Anna says, are there any real world scenarios where we prefer a microservice instead of an async common service? Like understanding that it's simpler and has less infrastructure and costs a fraction and all that.
Yeah, so a good example is like kind of the real world is there are cases in which we would ship out our microservice business logic out to end users so that they can do that work locally as opposed to having to go out to me to do it. And a very common thing I see like this is if you have a complex sales that you have to make that requires
Like
a human
Taylor Swift
being.
concerts, right? Like Taylor
Yeah,
Swift tickets. Yeah.
yeah, exactly. So you put those smarts on, like you push that smarts down, but understanding that when you do that, it's more difficult to update that logic because now it's over there and not over here. But it's still a perfectly valid way of distributing service, kind of service logic, is to say, is it better for me to put that logic on that person's device versus having it over here where they have to call an API? Like that, there's all sorts of trade-offs you have there.
Great. Awesome. Here we have a two-part question. Spanish, I'm going to translate it for you. Alexander says, data orchestrator, sorry, normally is an implementation of the business, or is there a tool that you can like parameterize, I think it's the word, so that orchestrator can wait for all the tasks that are pending for deliver the final result?
Yeah, so I didn't show any code at all for any of this stuff. Me in the .NET world, there are implementations, and these are the thing you'll Google for process managers. Some people also call them sagas. There are implementations of those out there in the real world, or in the in libraries and other systems like that. So in the Microsoft world, there are a few examples. If you look at like Azure Durable Functions, that's a form of these kinds of things. Other messaging systems like in Service Bus and Mass Transit have their implementations of these things, but it is like code running somewhere to do this work.
And our final question for today is Luis Robles, that he says, what are the advantages to use this pattern instead of async web API with anonymous messages, which is a lot less complex. It doesn't need an orchestration.
Yes, so the trade-off there is that with async web APIs, you're using synchronous, non-durable communication. And I say synchronous because the initiator is still waiting for a response back. So you just need to make sure that you're okay with that kind of interaction. In the case of where you're doing like a post to an API and they don't do the work right away, they can do the thing where they put they capture the details, stick it in a database, and then there's some kind of background process running that will then pick up those details and then act upon it. That's still queuing, but just using the database as a way of doing it, right? There's like a table with orders with an is processed flag. That's still a queue, but just like it's in the database now. So I am still thinking about those kinds of trade-offs. Like if an organization does not have messaging, then I will look at saying, well, let's just fake it with database. That's okay. Or using something like Hangfire, like it supports those kinds of things with its programming model. So I always look at those options and I say, no, nothing is off the table. I will consider each option and the trade-offs associated to say what is the best final solution there.
Perfect. Thank you so much, Jimmy, again for sharing all this. It has been a wonderful talk. And we also appreciate the attendance of all of you, the participants in our Save at the Fest event. If you wish to revisit this talk, please, you can find in our YouTube channel at Save a Software. We are also active on Facebook, LinkedIn, Instagram, and Twitter. If you want to check any other details on this agenda or other talks, please go to seva.com.co/seva.fest, and we invite you to join our next talk in the technical and in the methodological channel, which are about to begin. Thank you so much, Jimmy. Have a great day. Bye.
Bye.